How are we doing? All right. So I'll start today with questions. You have questions from homework or whatnot, Lucas? 9-2, number 21. Sure. All right, so here it says that to use Euler's method with a step size of 0.5 to compute y values y1, y2, y3, y4 for the solution of the initial value problem, y prime equals y minus 2x, where y of 1 is equal to 0. So we'll start with our formula for Euler's method. So this is just the formula. So our x0 is going to be 1. And then x1 will be 1.5. x2 will be 2. x3 would be 2.5. And then x4 would be 3. And I know that y0 then is 0. So y1 should be y0 plus 0.5 times f of 1 comma 0, right? Okay, so that's going to be 0 plus 0.5 times 0 minus 2 times 1. So that comes out to be -1. And then I'll just repeat the process then. So y2 is going to be y1 plus 0.5 times x1 comma y1. So that's going to be -1 plus 0.5 times, where is that formula? -1 minus 2 times 1. Oops, 1.5. So that's going to be -4, -2, so -3. And I'm just going to kind of continue grinding my way through this. Write it this way. Just forgot the F. So y2 plus 0.5 times x2, oops, I'm sorry, y2 minus 2 times x2. So that's -4, -7, -3.5, so it's like -6.5. And then y4 is going to be like y3 plus 0.5 times f of x3 y3. So it's -6.5 plus 0.5 times -6.5 minus 2 times 2.5. it's like -5, -11.5, so -575 plus that is -1225, I think. And that should do it. Does that feel okay? So again, it's like a recursive formula where you're using your previous answer as the input to the next step. And if we wanted to, like, we could plot this out if we'd like to get an idea of what this curve would look like. You know, where let's say each tick mark is like a half. So we had like 1, 0. Oops. So I have 2. And then I have 1.5, -1. And then I have 2, -3. And then I have 2.5, -6.5. You know, and like we get the idea, right? So just like each one of these is like a piecewise linear, but that's like what we're doing is that, and that curve should approximate the solution to that differential equation. Cool. Others with questions? From homework or otherwise, either anything is fine. As a build off of something Paulo asked about last time, I did check on the AP exam test format, and I guess the multiple choice sections are going to be on your, like through Blue Book or whatever, and the free response questions will be like displayed on Blue Book, but you'll handwrite answers to those, and they'll collect those to turn in. So it's like a hybrid exam. There is like a pre-testing module that you guys can practice on, and when it gets a little bit closer, I'll show you how to do that so you can run through and see what it'll look like and what the features are or whatever, so that it's not a surprise. But we talked about that yesterday briefly, and I just popped into my head that I followed up on that. I was surprised because that's different than previous years. Okay. If there's no other questions from homeworks, we're going to kind of continue plugging away. And the question that question 21 using Euler's method is a nice starting point because it's a way to approximate the solution to a differential equation. We've seen that we can verify what the solution to a differential equation is. In 9.1, we did practice that. 9.2, we saw we could like sketch a solution using like a slope field. In 9.3 and 9.4, we're going to look at like using calculus to like algebraically find a general solution or a specific solution if we have a starting condition to a differential, well, some differential equations. Again, there's a very deep area of mathematics where you could spend multiple courses studying like how to solve differential equations of different types. Here in this course, we're going to look at solving two different types. The first type we call a separable differential equation. These are going to be first order differential equations where we can factor out and get all the x's on one side and the dy dx, and all the y's on the other side. So, for example, if I have in general some function or some differential equation, dy dx equals f of x times g of y, what I'm going to want to do is I'm going to want to try to separate and get the x stuff on one side and then the y stuff on another side. So I'll divide both sides by g of y and multiply both sides by dx. So I'd have 1 over g of y dy equals f of x dx. Everybody feel okay with that? Some basic algebra stuff. now that I've separated the y's and the x's onto separate sides, I can integrate both sides, and we know how to do those problems, right? Ideally, right? So let's do a couple of examples. So let's start with the differential equation dy dx equals x squared over y squared. So I would start by multiplying both sides by y squared and dx. Everybody's okay with that? So that's going to give me y squared dy equals x squared dx. Feel good? Now we can integrate both sides. The antiderivative of y squared will be y cubed over 3. And the antiderivative of x squared will obviously then just be x cubed over 3. But I've forgotten something. Each time I did the integration, right, I should really have a plus c. Everybody's okay with that? Now, here's what I'm going to do. I'm just going to subtract like the c's onto one side. And I'm just going to call that new constant just c. Everybody's okay with that? In practice, you don't need to show that. You can just write plus c on one side or the other. Does it matter which side you put it on? No, man. It's just a constant, right? We haven't assigned a sign to it or a number or anything. Like when we figure that out later on, whatever side we put it on, like the sign will take care of itself. Everybody's good? Now, the only other issue might be do I want to clean this up at all so that the y is by itself? Probably. So let's multiply both sides by 3. Everybody's okay there? But 3 times c is just still a constant, so it's still going to just be, I'm just going to call it c. I can give it a different name if I wanted to, but like I'm just going to abuse the letter c to just, you know. And then we'll cube root both sides. So far, so good. Okay. So what I'm going to do now is I'm going to handle part B. So B says find the solution of the equation that satisfies the initial condition y of 0 equals 2. So what this is going to allow me to do is solve for C. So I can just say 2 is equal to the cube root of 0 cubed plus c. And I see then that c is equal to 8, right? If I cube both sides. So my final answer will be y equals the cube root of x cubed plus 8. You guys satisfied there? In general, these shouldn't be too bad, right? The hardest part is going to be getting to figuring out how to separate them, which could, the amount of algebra involved there can become more complicated than what we just saw in the simplest possible example. But they, you know, if it's a homework question from 9.3, they are separable. There will be a way to do it algebraically. So let's go ahead and do another example. Again, we're going to start by separating. So I'm going to multiply both sides by 2y plus cosine y, and then dx to both sides. So that's going to give me 2y plus cosine y dy equals 6x squared dx. Now that I've separated the variables, we can integrate both sides. What's the antiderivative of 2y plus cosine y? Y squared minus sine y. I think it's plus though, right? Because the derivative of sine is just regular cosine. And then equals, and the antiderivative of 2x cubed, and then tack a plus c somewhere. Now, am I going to be able to separate the y by itself here to write an equation like y equals? No, right? Because I have a y that's a polynomial and a y that's a trig. There's no way to resolve that into a single y. So there's nothing more to do on this one. Ideally, you'd like to have the y, one y, where it's like y equals, but that's not possible here because you have two different function types involving a y, right? One polynomial and one trig. Not going to be able to resolve that into a single y, so this is good enough. You guys feel good? Okay. Let's do another. So here we have y prime equals x squared y. Where's the dy dx? That's what y prime means, right? It's just like a, you know, what is the two things that mean, the two words that mean the same thing? Synonym. There you go. Thank you. They're like synonyms for each other, right? Just mean the same thing. So we'll do the same thing. We'll multiply both sides by 1 over y and then multiply by dx. And integrate both sides. The antiderivative of 1 over y is natural log y, almost. Yeah, natural log absolute value y. Yeah, I know. And the antiderivative of x squared, we've done that already. That's x cubed over 3, and then we still have the plus c, right? Let's go ahead and get rid of the, or get the y by itself. Since the y is involved in just like one place, we should be able to get it by itself. How am I going to get rid of that natural log? I use an exponent base. Which exponent base should I use for a natural log? E. So I like do the exponent base e to both sides. So it's going to give me absolute value of y equals e to the x cubed over 3 plus c. How am I going to get rid of the absolute value? Or I can just use just like a plus minus, right? Just like if we're solving an absolute value equation, you make one equation that's negative and one that's positive, right? So let's just do that. And then what does addition in an exponent mean? Means multiplication with the same base, right? Very good. Everybody's good there? And what we're going to do is we're going to collect the plus or minus and the e to the c. These are all constants, right? So I'm just going to do that. Everybody feel good? And that's will be our final answer. You guys feel okay on doing this? Relatively straightforward, right? A little bit of algebra, then just doing the same kind of integration that we've been doing all along. Could you run into it having to use a u sub or something? Absolutely, right? Could you have to use like one of your more complicated antiderivative formulas along with a u sub? Absolutely. But still just like the same kind of integration we've been going and doing the whole time. Everybody feel pretty good? All right. We're going to also do today 9.5. We'll circle back and talk about 9.4, but 9.3 and 9.5 pair so nicely together that if I'm going to do 2 lessons in a day, these are the 2 that I would choose to do because they're so closely related. 9.4 is like a specific example where it's like a rich example, so there's like a lot you can do with it, but it's just like a specific example. This is another technique section. So the second type of differential equation that we're going to learn how to solve is called a linear differential equation. So a first order linear differential equation is of the form dy over dx plus p of x, so that's a function in terms of x, times y equals q of x, just another function in terms of x. Everybody's okay? Keep in mind that when we say like p of x and q of x, that could just be a constant also, right? Like 3 is still like f of x equals 3 is still a function of x, right? So it could be something super simple even. All right. So let's look at a specific example. So here is a function or a differential equation. First thing I'd want to do is see if this is, as soon as I see there's addition or subtraction going on and I can't factor it into becoming a multiplication problem, I'm going to think that this is probably a linear differential equation. So I'm going to try to get it into the form above. So I need to get the y prime by itself. So I'll start by dividing everything by x. So if I do that, there's my dy dx. There's my p of x. There's my y. And as we kind of mentioned before, that q of x could be just a constant, right? Does everybody see how this is a differential equation or a linear differential equation? Now, if we try to separate this, what you're going to find is it's not possible to separate. These are still just going to be kind of stuck with a y stuck in the wrong spot, right? So even if I subtract that over and then divide by y, well, then the y gets stuck on this piece. Okay, well, I'll just subtract that over. Well, then you don't have dy times f of, or g of y. You know, like it will not, you can't separate it. It will not work by algebraic means. Which is a bummer that none of that stuff is going to work, right? So what are we going to do? Well, the key observation here is that if I take the derivative of xy, I have to use a product rule, which would give me like x times the derivative of y plus y times the derivative of x. And if I'm differentiating with respect to x, that's just 1, and there's no differential left with it, right? So that's what I observe here on the right-hand side of my equation. So if I rewrite that left-hand side as xy, or the derivative of xy, and then I integrate both sides, the integral just cancels the derivative, and then I can just do the antiderivative the other side, and everything is kind of like easy peasy. Everybody feel okay with what we did there? Now, the trick is like going to be getting that piece, right? So let's do this in general so we can set up like a form, because if it doesn't look like this, where it looks like the result of a product rule, we might have to multiply both sides of the equation by something to make it the result of a product rule. And that's what we're going to be kind of building up towards for the next few minutes. It'll eventually end in a formula. So what we're doing is like an exploration of like, how do we get to the formula? So don't like panic, because what we're about to do, you would not have to repeat on a test or a quiz. You'd have to be able to use the result of this, but I think it's helpful to understand the process to see where the process kind of comes in from. Is everybody cool with the plan? Okay. So let's take our general form first order differential equation, or linear first order differential equation. We're going to multiply both sides of this function by some I of x, which has a name. It's called an integrating factor. And we pick that I of x, let's say we know how to do that, such that this, the left-hand side, is just the derivative of I of x times y. We'll talk about how we pick that I of x in a moment, but let's say just accept that we can. So we've chosen our I of x, we multiply it by both sides of our equation. By definition, that left-hand side is just the derivative of I of x times y. I can integrate both sides. The integral cancels out the derivative on the left-hand side, leaving me with I of x times y equals that integral. And if I just divide by I of x, then I have that, right? Where y of x is equal to the integral of I of x times q of x dx, and then because that's, we'd get a plus c from doing that, divided by I of x. Everybody okay with that notion? So what we're going to do next then is talk about how we go and pick that I of x, right? You went along with me in believing that it existed, that we could find such an I of x. Let's talk about how we actually go about finding it, because that has not been addressed yet. So what we need is we need I of x times the left-hand side of our linear first-order differential equation to equal the derivative of I of x times y. So what I'll do is I'm just going to start by like distributing that through and then calculating that derivative. Everybody's okay? So I did the product rule to get that new derivative. So those are my two sides. Hey, I noticed that those guys go bye-bye. So P of x, I of x, y is equal to I prime of x, y. I can then, hey, look at that. I can divide that y out of there. So I have then that P of x times I of x equals I prime of x. And that, to me, now looks like a separable differential equation. So I can divide both sides by I of x to get P of x equals I of x times the derivative of I of x. If I integrate both sides, I'd have the antiderivative of 1 over I di is just the natural log of I. And that's going to equal to the integral or the antiderivative of P of x dx. And this should look really familiar. So it's like the last thing that we did here, right? Where we had 1 over y equals some function of x. Ooh! So it just turns into a times e to the integral of P of x dx is equal to I. And that is our formula that we're going to use to find our i's. Okay, so let's do an example here in practice. So again, first thing I'd want to do is confirm that I'm in a first order linear differential equation. So there's my dy dx. Here's my P of x times y equals Q of x. Everybody feel good? Okay, I'm going to begin by calculating my I of x. I of x is going to be e to the integral of P of x dx. So that's e to the integral of 3x squared dx. Which is just going to be e to the x cubed. Does everybody feel good there? I'm then going to take e to the x cubed and multiply it to both sides of my linear differential equation. By definition, the left-hand side is going to be just the derivative of e to the x cubed, aka I of x, times y. That's like the prime symbol. That's not to the first power. Maybe do it at more of a diagonal so it looks more primey. Is everybody okay with that? That's definitional. We've chosen I that guarantees us to do that. Just like when we do completing the square and we add and subtract like, you know, like b over 2a squared, right? And we know that immediately is going to factor to a perfect square because we made it so. Just the same idea here. So then we'll just integrate both sides. The integral just cancels out the derivative on the left-hand side. And then how are we going to integrate 6x squared e to the x cubed? And really, I guess we can write a dx at the end of this. There's a u subproblem, right? What should be the u? X to the third. So du dx is going to be 3x squared, or du is going to equal 3x squared dx, right? And hopefully what you notice is that 6x squared is just 2 times 3x squared. So I can do that. Did you guys see the substitution that we made there? We're okay? You can respond yes or no to these questions when I ask them. If you're not okay, we can elaborate more. It's no big deal. The antiderivative of e to the u is just e to the u, and then I get my plus c. So we got to put our u back in. And then last step will be divide both sides by e to the x cubed to get the y by itself. And that can be our final answer. Or you could write as c over x, or e to the x cubed if you wanted. Also, that's fine. Same difference, right? Let's do another, yes? Okay, I got a couple more queued up. So again, the first step is going to be to get it to look like a first order differential equation. So again, that form is this. Doesn't quite look like that the way it's written, right? So what do we need to do to get it to look in that form? That's the big complication right now. So I would divide by x squared. So that gives me y prime plus 1 over x y equals 1 over x squared. That's in the form that we're looking for. Everybody good with that? Okay, so the next thing we're going to do is we'll calculate our I of x. So that should be e to the integral of p of x dx. The integral of 1 over x is natural log. And now I can just write natural log x. I don't have to write absolute value of x. Why can I do that in this case? Why did I drop the absolute value? The initial condition tells me that x is greater than 0, so I don't have to do the absolute value there, which is nice because integrating absolute values stinks, which we'd eventually have to do later on. Integrating x, much happier with. Everybody cool why I didn't use the absolute value there? And that's a nice observation. You definitely want to have made that. So now we'll multiply both sides of our differential equation by x. And I'm going to go ahead and rewrite this as like, I guess it doesn't really matter. I'll just leave it as y prime. Whatever. You guys are good with it, right? So there's that. My left-hand side becomes I of x, or the derivative of I of x times y. And then I'll simplify the right-hand side. X times 1 over x squared is just 1 over x. This isn't looking too bad. Let's integrate both sides. On the left-hand side, the integral just cancels out the derivative. Again, the antiderivative of 1 over x is just natural log of x. I'll put the plus c over here. Again, I don't have to do the absolute value because x is greater than 0. Yes? So by definition, this stuff is the result of the product rule derivative of I of x times y. So it's always the way it is. Yep. So like if we go way back here, we chose our I of x so that when we multiply it by both sides, left-hand side is just the derivative of I of x times y. So that's definitional. You can make that, you can do that every single time, as long as we're choosing I of x the way that we're choosing it. Does that feel good? Yeah. Okay. And it's a good question, right? Because it looks like, why, if you just distributed that x through, I see the x times y prime, but this is xy prime, not x times y prime. You know what I mean? So it's the difference is annoying, but that's what's going on there. So then my last step would just be to divide both sides by x. No, we should. Right? Or you could write SC over X or whatever, however you want to write it. But we're not quite done, because if you notice in the beginning of this problem, they also give us an initial condition. That means that we should solve for C. We should have no C left in our answer. So let's go ahead and plug that in now. Oh, come on now. All right, so that initial condition was y of 1 is equal to 2. The natural log of 1 is 0. So we just have that c is equal to 2 then, right? So our final answer, y equals natural log of x over x plus 2 over x. said x, I didn't write it. Or 2x to the negative 1, whatever. Or you could write as one single fraction. Everybody good so far? It's going okay? You'll tell me? All right. I have one more example. And we can call it quits for today. Sound good? Okay. So I noticed that, hey, this guy is already in my desired form. Right? So I don't have to do any adjusting. So we'll just calculate our I of x. So I get e to the x squared. So I'll do this time so that we can emphasize this a little bit better. Okay. Now, the entire left-hand side simplifies down to I of x, or the derivative of I of x times y, right? Integrate both sides. The integral cancels the derivative. How do I do the integral of e to the x squared? Well, what u would I use? Okay, so du dx is 2x. Where's the other x that I'm going to have to substitute in? Guess what? Not an integral we can do. Right? The u sub's not going to work on it. We don't have an antiderivative rule for this. It's not one that we're meant to do. What should we write then? Well, I'm just going to write it like that and put the plus c at the end. And we'll divide by e to the x squared, and we're going to be done. That's as good as we can do. That's all we got. Is everybody all right here? For clarity's sake, what we did here in 9.5 with this integrating factor is not an A-B topic. This is a BC topic. If you were to take the BC calc exam, this would appear. It's not an A-B topic. I think it's worth doing because I don't think it's that difficult, and I think that, you know, if you're planning on being an engineering student, you're going to take a differential equations course, and you'll certainly do this, and it's nice to have seen it beforehand, so you're like, ooh, what's a integrating factor? Like, oh, I remember that. We talked about it for a day. Because I have a perfect memory. But this is not an A-B topic, so don't when it comes time for studying for the AP exam, this is not something that would be covered. Would I put a question like this on a test? Sure, absolutely. Because I think it's well within our capability of doing, but the AP exam can't be like all the calculus topics because there's only so much time. But I'm going to try here to be clear as to like what's a AP topic for the AP exam and what's not, because we're going to do a couple more things here in the coming days that are not AP topics that I think are good things to have done. They're things that you'll do in your first or second year calculus course that I think you'll be glad to have seen. And we have the time because basically having done the separable differential equations, we're kind of done with the AP content that we're responsible for. So we have some time. So we'll go do some of these other additional topics that I try to plan the time to be able to do because, you know, you'll be glad you've seen them when you're taking Calc 2 and going, how do I do trig substitution? It's like, oh, okay, I've seen this once before. It's, you know, or how do I do integration by parts? Well, I've done this before, you know, like it's not so bad. So we have the time for that. So we'll do a couple of those other miscellaneous topics here in the coming days. But this is basically the end of the AP topic. Okay. So the plan here for the rest of the test, you'll have these differential equation topics. I'm still going to talk about the population 9.4. I think that's worth doing. I'm not going to do 9.6. I think it's more complicated than it's worth. It's another example. If you take a differential equations class or like a biomathematics class or something, you would certainly talk about it. And then we'll do like some of these chapter 7 topics, these other integration technique. So we'll do 7.1, 7.2, 7.3, and then I have to look for where the and then 7.8 probably that'll be it for the semester of topics for us. After that, it'll be do and review stuff. So we'll just kind of pick a topic that you guys feel kind of shaky with. We'll do some review on that and then do some specific AP practice. And after we finish these last 4 sections or 5 sections I think I have outlined here and do the test, it'll just be you guys tell me what we feel weak on. We'll do some more practice on it. We'll reteach some stuff. And that's going to be, we'll take some portions of the AP exam in class where time permits. Go through some answers to those things if you didn't like after we score things and check them. Talk about some test strategy stuff, but basically we're pretty close to being into the, like my grade is kind of my grade. That part's done. So there should be okay. Nate? Yeah, we're gonna do it. I mean, I understand. I understand what you're asking.
Look, I'm like there.
I know.
I don't get this, and I take a test. It's gonna dive in.
I understand. We'll we got some more stuff to cover still. Like we'll revisit the idea, and we'll talk about formats and stuff when we get there. Okay. I understand. I know where we're at. I understand where we're at in the school year. I'm sympathetic to this. Okay, Michael.
So is this next test to be just from chapter 9, or is it going to have some of the chapter 7 stuff on it?
It'll have some of the chapter 7 stuff on it too. Yeah. yeah, would not be enough for me to write like a chapter 9 test. Only because there's not much, to do here. I will also say that here, if you check later this afternoon, I'll have some homework quiz stuff for chapter 9 starting to kind of populate into the MyAP site. I just haven't had a chance to like pull some questions together, but I can certainly do that here this afternoon. So if you check tonight, you should see the stuff for 9.1, 9.2, 9.3, and 9.5, and that'll probably be the last homework quiz stuff that we'll do, if that's okay with you guys. I think at this point you've done 300 or so AP multiple choice questions in that neck of the woods between the stuff I assign you for the, as the part of the test review stuff, and then the stuff we do on, through the site. It's an awful lot of stuff. I don't know how much more continuing to pick practice problems from there is going to be super beneficial, without like doing some reteaching on top of doing that. But yeah, I mean, it's kind of the plan here. So we're getting close to this being like in-class work only. We just have a couple more sections to kind of grind through, and then it'll be basically we're just going to be doing stuff in class, and maybe you get like, like a packet of like a practice test packet to like work through parts of at home, and then we'll talk about questions or go through stuff in class or whatever. But it'll be, we're close, guys. We're close. Hang in there, Nate. We're close. I'm done here for today, so you guys can relax. I think, what were the homeworks? It was 1 through 19 odd from 9.5, and 1 through 17 odd, and then 19 to 24 from 9.3. So again, not a ton of questions here. So stop.